Et on va reprendre avec Pierre Fraignaud du CNRS et de l'Université de Paris qui va nous parler de Distributed Network Computing.
Merci Rachid. Donc oui, pour aider, j'ai vraiment la précisé, maintenant c'est le nouveau nom. Alors je sais pas, il paraît qu'il y a un appel contre ce nom, alors je ne suis pas sûr qu'on va le garder longtemps, mais en tout cas, normalement maintenant on s'appelle l'Université de Paris, qui est le résultat de la fusion de deux universités, Descartes et Diderot. On avait du mal à choisir entre les noms, donc on a décidé de les enlever, ça s'appelle l'Université de Paris. So I switch to English. So I will talk about something which is slightly different from what Rachid has presented during all his lectures. I will really insist on the networking aspect. So there have been already several talks today, and in particular, for instance, this very morning, there was a talk about the brain in which the whole issue was try to collect what is the network of the brain. And in fact, if I want to say, let's say that's the vision of Rachid. It shows you the clean things. So this is a data center, whatever, that I grab on the web. So, but I want to go behind this data center, and behind this data center, you have this kind of things. And it could be even worse, can be like this. And I will try to deal with these dirty things. So essentially, here is the issue. So to summarize what has been presented in the lecture of Rachid and in many invited talks are standard models of distributed computing, and which are essentially the two most famous models are message passing and shared memory. And they are perfectly fine models. I mean, in the multi-core network, for instance, it's really a shared memory. Okay, there could be a bus or something, but you can really model it as a shared memory. Message passing, it's kind of an abstraction of a complete graph that everybody can talk to everybody, but this is kind of at a certain level of a network. It's true. For instance, in internet, you can establish direct connection between any two machines on the internet. You have seen also other type of models, like this type of model that was presented this morning by Jana and also has been presented by Carole Delporte during the talks of Rachid, which is kind of opportunistic exchange between nodes whenever they meet. But what I will try to address in this talk is what is behind this, and essentially what is behind the message passing model. I mean, what is, if you take, let's say, if you consider a network as a layer, like they do in networking, they really layer the model. So we'll kind of consider a model, a layer which is below. We'll really address that between two machines, actually these machines may not be directly connected, but there might be some networks in between. And this network might be structured. For instance, in parallel computing, quite often, at least in the old time, we would consider models in which a network has a structure because it was corresponding to the actual structure of machines. But now I will mostly consider arbitrary networks. There is no special structure like the internet. Okay, it has special properties, but there is no regularity like in this, for instance, four-dimensional hypercube that I displayed. So, okay, so what will be the model? Of course, the abstraction is a graph. So it's simply some kind of processing nodes that are connected by communication links. And in this type of model, there are really two issues that matters as far as communication is concerned. Not so much here, as in many talks, I will not assume any constraint. I will not put any constraint on the processing power of the nodes. So they could be Turing machine. In some lower bound, as it was mentioned in the previous talk by Sergio, there are some lower bounds that are still true, even if you assume models that would be more powerful than the Turing machine. But let's say that there are Turing machines. But there will be two concerns that related to the communication. One is latency. So latency is essentially the time it takes to cross an edge. And therefore, the time it takes to go from one node to a faraway node in the network. It will not be atomic communication or something like in an abstract model. Really, it will take steps to go from one point in the network to another point in the network. And the second important technological constraint is bandwidth. These links, they don't have infinite bandwidth. They have large bandwidth. With the current technology, it's really high throughput. Nevertheless, there is some limitation. So we'll have also to address the question of how much information can you carry from one node to one of its neighbors in, let's say, one time unit. And this bandwidth limitation it imposed some constraint on the type. For instance, again, if I take this topological approach that was described by Sergio, usually it's called kind of full knowledge protocol, that whatever you know at the next step, you will send it to all your neighbors, or you will write it, you will write everything in the memory. Here there will be constraint that you are limited to the amount of information that you can send at each step. Okay, so therefore there are two major issues that will be addressed rapidly in this talk. Is what can be computed by exchanging little information between nodes. And the second question, the second issue will be what can be computed locally. If we insist on only taking decisions based on what we see in our close neighborhood, the neighbors or the neighbor of the neighbors, but we don't want to go very far away in the network. So let's try to visit these 2 points one after the other. And let's start by what we can compute by exchanging little information between nodes. Okay, so let's take one example. I mean, it's one of the basic model problems, we want to address in this type of, we classically address in this type of problem, graph algorithm. We want to construct a minimum weight spanning tree. So we have a graph with different weights on the edge, and let's say that, for instance, you want to connect, you're an operator, you want to connect these different sites, and each time when you want to acquire an edge to connect two sites, you will have to pay a certain amount, which are these weights represented in this picture. And what you want is that you want to connect all these sites by paying the minimum. So the minimum will be to construct a tree that is spanning the whole network. Everybody will belong to that tree. And you will add the sum that you have to pay, I mean, the money that you have to pay for each edge, and that will be the cost of your tree. So you want this tree to be a minimum cost or minimum weight. So in this picture, this is the solution. And this problem has been addressed. I mean, it's a typical, again, a typical problem that has been addressed for many years. And these people, Guerraoui, Couton, Peleg, and Rubinovich in the 90s, they essentially showed an exact and tight bound on how much it takes to construct such a spanning tree. And this bound, so minimum spanning tree, can be constructed in, so D here is a diameter. Essentially, when you have minimum weight spanning tree, it's not difficult to see that there is no algorithm that can do the job without communicating at least through all the network. Here, there is no locality. You really have to go at distance diameter. But the important thing is how much information do you have to exchange between nodes? And this amount of information is square root n. So here the number of rounds. At each round, you assume that you can send, let's say, log n bits or polylog n bits between two nodes. So at each round, two neighbors can exchange information, but they can exchange only polylog number of bits. And the amount of rounds that you need, which means that the amount of communication that you have to do is square root n. So this bound, here I just mentioned it. I will not show anything about it. I just mentioned it because it's both an upper bound and a lower bound. The upper bound is quite interesting because it's a general technique. I mean, this type of approach they use, it's a kind of methodology. It's give a kind of methodology that has been used to solve many other problems. And interestingly, these lower bounds, the fact that you really need at least square root n, it connects distributed computing in this framework with communication complexity. Communication complexity, it's a vast field of theoretical computer science, and this is a strong connection between this type of distributed computing models and communication complexity. And to illustrate this tight connection between the two domains, I will take another simpler problem to explain, which is cycle detection. So cycle detection, again, is a classical problem because if there is a cycle, there might be deadlocks. If it's a network and there are cycles, it means that the message can loop forever. And so you want to detect cycles. If it's a database, also it means that there are references that are in a cycle. You want to avoid this. And I will here address only the detection of 4 cycles. Cycle of length 4. Is there, so the question is, in this network, is there a cycle of length 4? If you look carefully, I mean, it's not difficult to see that I think that in this network there is one, here there are actually many. And the question is that the nodes, they need to determine whether or not there is a cycle of length 4, one or many cycle of length 4, in a distributed manner by exchanging as few information as they can. And the rule is as follows. If there is no cycle of length 4, which is not the case in this picture, but if there would be no cycle of length 4, then all the nodes should be happy and accept. Instead, if there is at least one, again, this is the case here, then at least one node should reject. Many nodes can reject, but at least one should reject. That's the simple rule of detecting or deciding about the legality of this configuration. Okay, so what is the result about this? The result about this, which was proved in 2014 by Drucker, Kuhn, and Oshman, it was that cycle detection requires at least square root n bits of communication. So, and in fact, it's tight. I should mention that this is actually, there is an algorithm, very cute and nice, simple algorithm that reached this bound. So square root n, again, you need it. And the reduction of the problem, now I will try to quickly explain, is about, it's a reduction, as I said, to communication complexity, and it's a reduction to set disjointness.
If you have C3 instead of C4?
We accept. We are really looking for C4.
No, if you change the problem and ask for...
I will mention that. I will mention that in a minute. Indeed, it changed the game, actually. So I may already mention, I will come back to C3 later, but I can already mention that if you look for C6 or C8 or this type of reduction, you will see that it will carry immediately. It will change the exponent, but you will, if it's odd, it's a little bit more tricky. The case of C3 is very particular, triangle. So, but I will mention it. So the reduction is as follows. So what is the problem disjointness? Imagine that you have two friends, Alice and Bob, and they want to organize a party by inviting people, and they invite people from a set of M people. So let's say that they are the M friends in the school. And they have already invited some people independently, and at some point in time they call each other and they want to know who they invited, and they want to avoid that to invite twice the same person. And the question is, how could they manage to know who they invited? How much information do they have to exchange to know who they already invited? So for instance, Alice already invited Nir, Sergio, Jana, and Michel, and Bob invited Ellie, Ahmed, Sergio again, and Valerie. And they want to know whether their list is distinct, is disjoint, the two lists are disjoint, or whether there is someone belonging to the two lists. And a famous result of communication complexity is that they have no option in terms of worst case. There are cases of subsets for which they need to exchange at least m bits, which is essentially to say they need to say for each person in the school whether or not they invited them. So that's the result. Take it for granted. That's a very famous result of communication complexity. And let's try to use it to show our lower bound. So the reduction is as follows. We'll go very quickly, it's just to give you a flavor. So the reduction goes as follows. Alice and Bob, beforehand, before starting solving the problem, they will agree on a graph G, which is C4 free. And this graph G will have m edge, where m is the number of elements of the ground sets that they have their element from. And this m, it's known from extremal graph theory that there are graphs which are C4 free and which contain n to the 3/2, n square root n edges. So they agree on this graph beforehand. Now, what do they do? So these are the set of edges of this graph, E1, EM. So they build in their head, they build this graph, this big graph, which consists of 2 copies of G, and actually 2 copies of the nodes of G, not yet the edges, 2 copies of the nodes of G, and a perfect matching between the same node. Now, this is the thing they agree upon. Now, on each side, then independently, depending on the inputs they receive, so Alice receives some inputs, a set of friends she already invited, Bob receives a set of inputs, the set of friends he already invited, And what they will do, they will add in this graph G, if they have already invited this person, let's say the JICE element, let's say they already invited Ellie, then they add the edge corresponding to Ellie in the graph. And this is not difficult to see that, for instance, Sergio, that was belonging to the to list, Sergio will be added by Alice and will also be added by Bob. And therefore, we will have the same edge that will occur in both sides, and it will create a cycle, a C4. And this is not difficult to see that this is the only way to create a C4 because G contains no C4. So in fact, what they will do, Alice and Bob, they will do these things. They will add independently on each side, they will add their edge, and they will run the supposed to existing C4 detection algorithm. They will simulate it. Whenever two nodes have to exchange, two nodes in the same copy as to exchange message, and then they do in their head. And if two nodes that are across the two copies, then they will send the message to the other party. And therefore, since there are n bits, n links, so we should have that the ratio of the two should be at least square root n, because we know that we cannot solve set disjointness by exchanging less than square root n information. So that's essentially the reduction. Whether or not, I mean, you get the detail here, it's a very simple reduction, very nice. And it shows here the tight connection between communication complexity and distributed computing in this model, in which we are bounded to send only a limited information between nodes at each round. Usually, all the lower bounds we know are essentially of the same type. So it might be more difficult, more complex to build, but essentially that's the same thing. You take a problem whose complexity is known in the communication complexity setting, and you try to build up a setting that corresponds to a graph algorithm in which if you could solve this problem faster, then you would solve the communication complexity faster. So what is essentially the state of the art of this kind of wide class of problems? So the methodology for the design of efficient algorithm, I would say it's quite now well understood. People are able to design very efficient algorithm in this model. And the main things, the important fact to remember is really the tight connection between this model and communication complexity. And this is true also including randomization, because there is also the theory of communication complexity when you allow randomization. So also you can design extremely, I mean, it's for the design of lower bounds. You can use results from randomized communication complexity to get a lower bound in the model. Some problems resist, and as it was mentioned by us by Uri, triangle detection is one of these models. There have been progress in both directions. Finding a lower bound is much more complex. For two parties, difficult. You have to use other type of model of communication complexity, and the complexity of triangle detection is not yet completely understood. What is interesting is if the graph now is not arbitrary, but the graph is a click. So now you go back to the kind of message passing model, but you bound the amount of information you can send on each link. Surprisingly, the problem becomes extremely difficult. And in fact, it was shown that there is a strong connection with circuit complexity. And if you could design lower bound in the congested click model, you could design lower bound for circuit complexity that are problems that are resisting for more than half of the century. So this seems that it's an extremely difficult problem to design lower bound in the congested click, because it's difficult to have a discut and so on. So I move on with the second part, which is what can be computed locally. So now it's a different setting. I can exchange as many information I want between neighbors. The only thing I want is that I want to solve problem locally by exchanging only between people or machines that are close to me, or maybe in the brain between cells that are not too far away in my brain. So this is, for instance, a map of the internet, which again looks a little bit similar to the map of the brain, I don't know. But so you want essentially to solve problem by avoiding communication with faraway nodes. You want to solve problem by communicating only with your close neighbors. So for example, what kind of problem? So this is another typical, maybe the classical problem, the same way MST was the problem for the previous model, is coloring. So the input is just the nodes. Okay, the nodes, I forgot to mention, but the nodes, they have IDs, like we have IP address. So the nodes have IDs. And what they want to do is that they want to compute a coloring, let's say to avoid interference between nodes or whatever. And so you want that each node should pick a color which is different from the color of all its neighbors. And there is this lower bound that was proved in the 90s, which shows that actually this problem, I mean, coloring, even if you allow coloring with a large number of colors, your degree, maximum degree plus 1, it cannot be done in constant number of rounds. Even though the specification is completely local, I mean, it's just something simple. I mean, you should communicate, should have a different color from your neighbors. You need to consume at least log star n rounds. And this is a very interesting and very strong lower bound for two reasons. One, it doesn't use the basic, I mean, there are many, many lower bounds, but they are kind of trivial in some sense. It's just that, for instance, for MST, you can easily show a lower bound for minimum weight spanning tree because you can show that diameter is required, because you need, it's kind of indistinguishability argument. It's very simple. But this lower bound is not at all of this kind. It's a very sophisticated lower bound, very nice. The second reason is that this is the only lower bound, only non-trivial lower bound we know in this setting. So, and this is even more impressive when we see compared to what is the best known upper bound, which is 2 to the big O of square root of log n, which is something which is in between the polylog and the poly. So there is a huge gap between this kind of very, very small, it's not constant, but still very, very small thing for, let's say, if you take the number of atoms in the observable universe, it will be something like 5, so very small function. And this is still grid larger than any polylog. So there is a huge gap, and this gap exists for more than 25 years.
So for which delta is this lower bound?
Delta here is the maximum degree of the graph.
The lower bound.
The lower bound is, it holds even for the ring. So if you take 3 coloring, you want to color the ring with 3 colors.
The upper bound.
Oh, it's for arbitrary delta.
But if delta is fixed, then the lower bound is tight.
So delta cannot be fixed. If delta is too small, the graph will not be delta colorable. So, sorry, if you fix the delta, and you say for the class of family of maximum degree delta, okay, so if you do that, actually, okay, that's good. It's almost, because we have the best result, actually. So the best result is log star plus delta to the, so it's a square root of delta. So it's log star plus square root of delta, if you take as a function of delta. And again, we know that has been a huge competition. Each year, almost, there is some result which is faster and faster. But yeah, as a function of delta. So as a function of n, log star appears, but it seems that delta matters, indeed.
But when you say the upper bound, the algorithm knows n.
This one, yeah, the algorithm knows n.
You sort of dismiss it, but the algorithm knows n. Why locality? Where do you know?
Yeah, that's
the brain and the internet.
You're completely right. It's a pain to say this to Eli, but he's right. He's right. So it's yeah, it's always a debate, because it facilitates a lot to assume that you know n. Not knowing n is a pain. You have to guess it. You have to try and try. I mean, it makes the whole machinery complicated, but it doesn't change the nature of the complexity in some sense. So it makes things much more complicated, but in terms of the nature of the problem, doesn't change much. So just to mention quickly that we have the same type of things, like, for instance, in shared memory, in asynchronous computing, deciding whether you can solve in T rounds, that is to say, by communicating at distance at most T, it's undecidable. There have been interesting thresholds that has been identified in some families of graphs. For instance, there is nothing between constant and log star, nothing between log star and polylog, nothing between. So it's really, there are, I mean, quite a lot of things are known in this model.
Here, the decidability is by reduction to what kind of halting function?
Can I take this question offline after? No, I don't remember. And there is even the notion of completeness in this setting, at least for certain class of problems. I mean, those whose solutions are locally checkable and also that are greedily constructible. And this, for instance, this problem here that I will mention has been identified to be complete for the class of problems that you can solve in polylog number of rounds. So what is the problem? You're given a bipartite graph, and you want to color one side of the bipartite graph, let's say the bottom side, by 2 colors, such that each node is adjacent to 2 different colors. That there will be essentially the same number. I think I take green and red. There will be essentially the same number of green and the same number of red neighbors. You have to do some assumption on the degree. This is a problem that would be trivial to solve if you would have access to randomization. I mean, you just pick a color at random and it works with high probability. Now, if you want to do it deterministically, nobody knows if you can solve this problem in polylog number of rounds or not. If you can solve this problem in polylog number of rounds, then essentially you can solve a huge class of problem in a polylog number of rounds. So this was a very nice result by Ghaffari, Kuhn, and Moss in 2017. Yeah?
So it means that you have a notion of distributed reducibility.
Yeah. Yeah, it's you reduce by polylog, again, everything by polylog number of rounds. That's the notion of reducibility. If you would have a solution to this, in a polylog number of rounds, you could find a solution to the problem, all problem in this class, including actually coloring in this class. So if you want to show that you could solve coloring in the polylog number of rounds independently for all delta, then if you try to solve this problem, you have the result. Another connection which is interesting is with fault tolerance, and in particular with self-stabilization that has been already mentioned several times. Actually, there have been talk on self-stabilization by Sébastien Tixoy during Rachid's series of lectures. I think time is going, so I will not mention exactly these things, but there is a tight connection between local computing and local decision, which is the ability of detecting whether a configuration is legal or not, and the fault tolerance computing, and in particular self-stabilization. So what is the state of the art? So essentially, we know more and more how to do to construct solution of what is called locally checkable labelings, like this problem I mentioned in the bipartite graph, like coloring, like maximal independence set. All these problems are in this class. There is a notion of completeness. It is pretty well now understood how to de-randomize, so there is also a notion of de-randomization. There is also a fruitful theory that developed about distributed decision, and recently there have been even results about mimicking what has been done in interactive proof system to do it in a distributed manner. The point is that it remains that it's extremely difficult to find lower bounds. So for instance, again, the lower bound about delta plus 1 coloring, the only lower bound we have is this lower bound by Nati Lineal. And at this point, despite intensive research on the field, no better lower bound is known. So, to conclude, I would display the world of distributed computing a little bit like this. Like we have a lot of work that has been done, and essentially distributed computing essentially started by studying timing issue, which are essentially asynchrony or failures, or whether you include failure into asynchrony, whatever. You model asynchrony by adversary or by daemons. And this is, of course, the whole topics, many rich, that has been taught by Rachid and during these lectures. There is another community which is interested in what I essentially summarized today, which is a spatial issue. What's going on with the network? What's going on if we have constraint on the throughput, on the latency, and so on? And there are work at the intersection, but this is really thin at the moment. Let me mention, for instance, there are notion of synchronizers. So if you have an asynchronous, if you have an algorithm that has been designed for a synchronous network, and you want to run it in an asynchronous network, there is an automatic way of doing it. Although it should be a failure-free network. So you can deal with asynchrony as long as there is no failure. Another type of approach here is what I said, is self-stabilization. Self-stabilization, I mean, has a notion of failure. It's not crash failures. It's just failures that the nodes recover after a failure. And there are other works here at the intersection that remains a little bit not very populated. Maybe one way to reconcile the two would be to adopt a higher perspective, like Sergio mentioned in his talk, which is try to apply topology and try to understand what's going on here when we use the topological tool. There is no obstacle, I mean conceptual obstacle to that. There is, however, two main issues. One issue is that you will have to deal with the structure of the graph, and the structure of the network will have a huge impact on the simplicial complex that you will have to deal with. So it makes the problem even more complicated. And the second issue is that they are not full information protocol, because we want to deal with limited bandwidth. And again, this is kind of difficult to deal with topology if you incorporate the fact that the algorithm is not sending everything it knows at each round. So it might be one direction, which is, I think, very worth to try, but it might be very, very difficult. And through this, I conclude my talk.